Hello, Mr. Aaron, Mr. Ryan, are you right?
Yeah.
Okay, so let's look at these numbers. 2, 4, 8, 16, okay? So we are given a list of integers, positive integers, and we want to find out the product of it, right? So we times it together. What's product?
Times all numbers together.
Product, this is array, right? We're given this.
Which is 64 times 16.
Yeah?
64,
What's this number?
64 times 1024.
1024, okay?
I think.
Yeah, 1024. That's right. For example, like this 1024 can be represented as 2 to the power of 10, right? Okay? This is the prime number. So we want to find out the distinct number of the prime number, right? Which is 2. So you return 1. Let's take another example.
2, 4, 3, 7, 10, 6. 2,
4, 3. It doesn't have to be in ascending order, okay? 7, okay? What's the answer here?
24 times 7.
Is it 168?
So what's this number?
Is it?
Is it 168?
It's 24 times 7, I know.
Is it 168?
I don't know, let's check.
Is it?
Eight,
Yeah, probably it is 168.
Okay, so 168 equals 2 to the power of
2 times
3 times 3, 7. Is it? So how many numbers? 1, 2, 3. So we return 3 numbers. Okay, so what's your thoughts about solving this problem?
I just do the maths. I do 2 times 4, 8, 3 times 7, 21. No, 20, yeah, it's
We
20.
modulus.
And then just times them together.
You want to calculate all the numbers, the product,
Yeah.
right? And then, okay, so once we have this number, so what do we do? Yeah, we given this.
I don't know what we do with money.
What do you call this process? 168 becomes that. Then we call it
Modulus.
factorization, right? Integer
Division.
Why is
factorization.
it to the power of 3?
2 to the power of 3.
Why?
Each integer, yes, that's a good question. Each integer can be represented as P1A, P2B times together, okay? So these P are the prime numbers. A, B, C, this is non-negative integers. Why is it 2 to the power of 3? 2, this is already a prime number. 2 to the power of 1. This 4 is 2 to the power of 2. 2 to the power of 1 to 2 to the power of 2 equals 2 to the power of 3, okay? And 3 and 7 is already a prime number. We can convert integer back to this format, right? We call it factorization, okay? Your solution is that we find out the product and then we do this process, right? Do this process. So 168, we just try if it can be divided by the first prime number, which is 2. If it can, then 168 divided by 2. This is 2 times 84. 84 can be divided by 2. So this is equal 42 times 2, right? 42 can be again divided by 2. Is 2 times 21, right? Okay, so look, how many 2's? 3. Okay, so what's the next number? Because it can't be divided by 2 again. So what's the next prime number? Which is 3, right? So 21 equals
7.
3 times 7, okay? Okay, now with the remaining 7, we keep this process until it reaches 1, right? Make sense? Okay. So one question. This number could be very big. Do we have to find out the product?
No.
No, right? We don't have to put.
Otherwise, why would you ask that?
We are given this array, right? We don't need to multiply together. We just have to find out the factorization of this number and this number, this number, this number, and then we find out all these p distinct prime factors and then put it in a set. Then we count the number of the distinct because set only stores the unique numbers. Am I right? Yes. Does it make sense? Okay, so let's repeat this process. Okay, let's take a look at a more complex example. 2, 4, 9,
8.
10. 8. Okay, so one approach, your approach is times it together and do this process, right? But this number could be very big. So how do we do it? Look, this 2 to the power of 1. This 4, 2 to the power of 2. This 9, 3 to the power of 2. 10, 2 times 5, right? 8, 2 to the power of 3. Okay? So we just look at this number. How many 2's? 1, 1, 1, 1. Okay? That's 2, that's 3, and that's 5. So we return 3. Does it make sense? Our task is to multiply together, right? We multiply together, we're still doing the same process, right? So we don't have to multiply. Does it make sense? Okay, so if we multiply it, what's the number? A 72. 320 times 8, right? Times 8, that could be, I don't know, But once you get this number, you do this reverse, right? You do this reverse.
5760.
So, and write this number, eventually you go backwards, right? So there's no point to multiply because we already know what numbers comprise of it, right? Okay?
It's 5760.
5760. Okay, so this number is 2 times 280. And then again, this number 2 times 1440. This number, how many 2s, right? 1, 3, 6, right? You keep doing this, right? Yes?
720.
Yeah, I know. You eventually will get the same result. Okay, this is one approach, obviously. So we need to think about how to improve it. And we're going to talk about the improvement in the next lessons. Okay. Define, let's say, f function. We're given these nums. We put all the prime factors in a set, right? We put all the prime factors in a set. Let's say a equals set. It's a data structure, yeah?
Yeah.
What's the difference between a set and array?
Array is array and
A set, what's set? Stores a unique, it's a hash table, right? Stores a unique number, right? We want to find out the number of distinct factors, okay? Yeah, does it make sense, right? We go through each number, right? X in numbers. First prime number, let's say, is 2, right? P equals 2. Why x not equal 1? Why x can be divided by the p, right? Can be divided by p. Then we put this prime number in the hash set, right? This is a hash set, and then x divided by p, right? So this is basically saying that if this number, if this current number can be divided by p, which is the prime number, then we keep dividing it, right? Okay. And if we can't divide it by that, then we try the next prime number, p plus equal 1, okay? And, okay, we try the next number, then return the length of a. Can you spot any, problems here, or any questions here so far? Okay, I'm telling you, this is the prime number, right? This is p prime number. And if this number is not 1, then we check. If it can be divided by this prime number, then we keep dividing it. And then we put this p into the set, because this set stores the unique numbers, right? Unique number, so we finally return the length of the set, which is the distinct number, right? Okay? So any problems here? Any questions? I mean, it's not a problem, but any questions so far? What's p?
Prime number.
Why is it plus 1 here?
So you can plus 1 to the prime number. So next prime, if you find next prime number.
Plus 1 is the next prime number?
No.
Okay, so that's the problem, right? Your plus 1 is not the next prime number, right? Yeah, because 2, what's the next?
3.
What's the next?
4.
Right? Do we need to check 4? No, right? 5, right? Yeah? So because this p, we try to let it represent the prime number, but here we just plus 1. But this approach still works because it just keep doing 2, 3, 4, 5. It's just doing some useless work when it's coming to 4, coming to 6. Because look, when p equals 4, there's no point to do this, right? There's no point to do this. When p equals 6, there's no point. No point. Why is that? Because when p equals 2, it's already checking if it can be divided by 2. And then if it can be divided by 2, it would just repeatedly divide it, right? So when it gets to the 4, there's no point, right? Does it make sense?
Yeah.
Okay, so let's take an example. 8. So look, it comes to this. You can divide it by 2, 4. Divided by 2, 2. Divided by 2, 1. Right? 1 which is 1. That's it. How do we find all the prime numbers under 100?
You just basically
1, 2.
you check it every timetable and then cross it out.
Yeah, that's the diagonal I'm talking about. Right? 1, 2. Why I don't know the name, right? Okay. Okay. Suppose that this is 100, right? So first of all, 1 is not a prime number, cross it out, okay? Okay, 2. 2 is a prime number, we cross it out the multiples. Okay? Next one. 3, we cross out the multiples. 6 already crossed out. 9, right? Etc. 5, you do it, and the remaining is the prime number, right? Yeah? Okay. So this is similar idea, okay? This is the similar idea, right?
yeah, but when you check 3, you're gonna check 6, which is already crossed
That's
out.
right. When it's crossed out, it's crossed out, right? A number cannot be crossed out twice.
Yeah, I'm saying you're doing useless work looking at a 6.
Yeah, I know, but this is still the most efficient algorithm to find all the prime numbers under the range, given the range, okay? So one improvement you can imagine is that instead of p, right? So how about if I can get the algorithm iterate? So we pre-calculate the prime numbers. If these numbers are given a range smaller than 1,000, right? So if all the numbers are smaller than 1,000, then we find out all the prime numbers under 1,000, and instead of incrementing 1, we just get the next prime number. Does it make sense? Yeah? So instead of p equals 2, what's the next number here? P plus equal 1. That's not very efficient. We say, get me the next prime number, which is 3. Get me the next prime number, which is 5. Get me the next prime number, 7. And what's the next number? Prime number?
11.
11, yes? Instead of plus 1, you can get this, right? Okay? Okay, so what have you learned today? We want to find out the distinct prime factors of the product of an array. Do we need to find out the product of an array?
No.
Why?
Because we could just count if we could divide it by each number and then count how much numbers are in that thingy and then return how much numbers are in that you counted.
Okay, so we want to find out the distinct. So how do we find out the distinct here?
Set.
Yeah, set, hash set, okay? Set stores a unique number, okay? So, for example, like a equals set. A dot add 1. A dot add 2. A dot add 3. Okay, what's the length of a? Adding 1, adding 2, adding 3, adding 3, adding 3. What's the length of the a? The set stores the unique numbers. 1, 2, 3, 3, 3. 3, okay? A equals a list. A dot append 1. A dot append 2. A dot append 3. What's the length of number of a? How many elements in a? 1, 2, 3, 3. How many elements in a?
5.
5, okay. So if I change this to set, only 3, right? Because 1, 2, 3. 3 is a duplicate. It doesn't go in. 3 is another duplicate going. Make sense? Yes?
Yeah.
Okay, that's it for today. Bye bye.
Bye.
Bye bye.